Due to the geographical characteristics of Stuttgart, there were difficulties in the construction process. Let's look at the foundation and structure of the Mercedes-Benz Museum. The site of the museum is a former quarry filled with mineral like limestone, and mineral waste is stacked up, and they are involved in the foundation working conditions of the building. And long after the massive bombing of Stuttgart during World War II had to be checked for remaining bombs before the commencement of any site work. Therefore, the original shallow foundation design plan had to be abandoned when it was encountered miscellaneous fill material during excavation. The foundation working on the site of the Stuttgart is subject to a number of conditions. The ground and mineral water bearing stratum is located about 40 to 50 meters below. Furthermore, we are discharging the mineral water system in the Stuttgart area is the second largest in Europe. Therefore, the wells of Stuttgart groundwater represent a subject of protection given highest priority. When you are deep in the filing, both groundwater source and fluoride can increase in aquifers, and contaminated soil and limestone can increase hazardous substance in groundwater. Sediment can occur in groundwater on unexpected erosions caused by aquifer deformation, which can lead to sinkholes. Let me explain the process of foundation piling at the Mercedes-Benz Museum, which follows these difficult conditions. The foundation of the Mercedes-Benz Museum is carried out through the following process. Prior to piling, the installation of the piling rig is studied as follows. They use Frankie pile method, which are in-situ concrete driven piles with retrievable casting tubes, to withstand a sufficient load with a relatively short pile. First, set driving pipe in place, fill in stopper concrete and ram in. The hammer is attached to the driving pipe as shown in the picture because it uses a free-fall pile hammer. Ramming in the driving pipe, draw inner ramming with free-fall pile hammer. The tubes are fitted with a waterproof seal at the foot in the form of the plug or dried concrete or gravel sand. Hammer is applied to the concrete, driving it outwards toward the bottom of the pile and forming a mushroom-shaped base at its point, a cylindrical river. After reaching the desired depth or ramming criteria, the plug is detached and the necessary volume of footing concrete is driven in. Therefore, the expanded pile provides sufficient friction force for a short length. Next, a reinforcement case is inserted, concrete filled in and a casting tube is retracted. Reinforcing case provides the structure with stiffness, allowing withstanding tension, bending, torque loads. After additional concrete is added as follows, the casing tube is recovered. Finally, capping the pile head, arranging the connecting reinforcement. As we use Frankie pile method, we can reduce the impact of the problems mentioned earlier. one pile created like this. Come together to support the Mercedes-Benz Museum above 850 piles. A slab is placed on these piles to transfer the load to the pile. The slab has 3 cores, and this core has a larger load. Therefore, slab under the core is thicker than anywhere else with a larger load. The architecture's transitions are fluid. They are not right angle nor straight walls. The wall transforms smoothly into a ceiling or room. This was made possible by double helix curves components known as twist. The Benz Museum transfers loads through the main core to the foundation. The 3 main cores are located in the center of the building. The following architectural elements are created sequentially and are connected to the core to transfer the load. Miss ramp is not only an access element, but also an important load-bearing factor in relation to twist. If you look at the cross-section of Miss ramp, it is designed as a hollow box girder and serves as a curved beam. This transfers lip and sailing loads to the main core and support. Due to the void space 30 meters high, because the red zone is void space, there was less space to display cars. That is why it is designed to display the maximum number of vehicles at its location. Therefore, the load on the slab increased due to the number of vehicles. Especially considering the wheel load caused by the truck. There were trap truck loads approaching in one room, and up to 4 tons of wheel load had to be considered as user requirements. To solve this problem, they reinforced 2 meter space H steel beam under the slab. It effectively delivers the weight of the slab, vehicle, tourist, and other loads to the sub-support and main core. And finally placed a 50-100mm reinforced concrete slab. The twist forms a striking transformated element throughout the building. As a key load-bearing structure, the twist supports exhibition levels spanning more than 30 meters without intermediate columns. The top surface of each twist becomes a circulation lamp that seamlessly transitions between the staggered galleried planes. The twist consists of the box girder rotated about its own axis with double curve size. If you look inside, it has a comparatively complicated internal load-bearing structure with individual crossbars. There are some problems with the twist. First problem is the linkage to the core is not sufficient. So, a satellite core as additional supports are also required. 2 bulkheads between the core and the satellite bears not only the weight of the twist but also the miss and collection floor. Second problem is that the entrance through the twist is needed to install vehicles in the exhibition. There is a lot of load going on as the vehicle passes by. This picture shows the side of the twist. At this time, to install the entrance in the middle of the twist can cause cracks as the moment load on the center increases. In consideration, the entrance was installed next to the core. Today, we focused on structure. Next, we will be studying the ace part, exterior. Today, our reference. Thank you for listening.